So, welcome back to the second session concerning combustion chemistry. And you have heard a lot about this topic again in the morning in the part of Professor Sahu. So there is, of course, some overlap, and sometimes it's important to get a different point of view on this topic. Especially if you are not familiar with it, I think it's very helpful so to get this explanation again, also from a different person. So I was really happy to see it in the morning. So in the last part we have discussed more the background. So we have discussed elementary reactions, global reactions, chain branching, chain propagation, chain termination, and so on. And now we want to put all these things together to get an reaction mechanism finally. So again, we have our simple system here. H2 plus half O2 gives water. We have our elementary reactions propagating, branching, and termination. So first of all, why is this so important to consider the chemistry? So one simple example are the classical ignition limits, or sometimes also called explosion limits. So we have in classical PT, pressure temperature diagram, and here we see the ignition limit curve. So at conditions left of this curve we don't see an explosion, and right of this curve we can see an explosion. And this is very typical, and for most of the combustibles you see a similar result, of course, at different pressures and temperatures. But you see that if you sit on a specific temperature, here for example 800, and you increase the pressure, you start with no ignition and low pressures, then you come to an ignition region, and again at higher pressures suddenly it do not ignite anymore. And again, finally, you reach a third limit. And this is due to the interaction of mainly diffusion and chemistry. So at the very low pressure, the molecules, so we have very few, or we have a very low density at low pressure, and so the molecules diffuse to the walls, towards the walls, and at the walls they are more or less quenched. And so if you increase then the pressure, the density also increases, and therefore you have more collisions of the molecules, and then you are in a region where you have ignition, and then suddenly at around 100 millibar you find the next limit. So suddenly at higher pressures you don't see any ignition anymore, and this is then now a competition of chain branching and chain terminating reactions. So the reaction H plus O2 leading to HO2 is a third body reaction. So a colliding partner is involved, and of course at higher pressures these collisions occurs more often, and so this competition between the formation of OH and the formation of HO2 at this point decides no ignition takes place. And then if you increase pressure further, you come to the third limit, the thermal ignition limit. So here density is so high that you produce so much heat per volume that ignition always takes place. So when we look now, for example, at temperature dependency at high temperatures, this is the most important reaction. So H plus O2 gives O plus OH, so chain branching, and this is the dominant reaction at high temperatures. Above 1200 K, this dominates the ignition process, and so the flame propagation and the ignition are both very sensitive concerning this equation. At intermediate temperatures, we have to consider this third Berry reaction, H plus O2 plus M leads to HO2 plus M. So this is then the reaction with is in competition with the formation of OH, and this is the dominant reaction here, and also we have to consider this H2O2 decomposition as it leads finally to the formation of OH. So this HO2 plus, in case of hydrogen leads to hydrogen peroxide, and this hydrogen peroxide then decomposes, forms OH. So this is then at intermediate temperatures for a lot of species the dominant reaction. And then lower temperatures, for hydrocarbons especially, we have to consider very complex chemistry. So we have the formation of peroxides like described here. So it's very, 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 very sensitive concerning a lot of reactions. And therefore, so the high temperature part is easy to describe. So we need to know mainly this equation in detail, and then the rest we just have to guess some numbers. Normally that's enough. For the intermediate part, we have to consider some more reactions. And if we have to consider lower temperatures, then chemistry becomes more and more complex. And we have to consider more and more reactions. So of course then the question, we have this H plus O2 gives O plus OH. This is the important reaction. But okay, where do these H atoms come from? We have H2 plus O2 at the beginning. So of course we have always fuel decomposition. So especially at higher temperatures, some H radicals will be formed. So of course different fuels have different decomposition rates. So we see different ignition delay times for different fuels due to this different H atom formation rate. So for example, methane, C plus 4 hydrogen atoms, atoms it's very difficult to ignite because it's difficult to abstract the first hydrogen atom. Propane is much easier to ignite because it's easier to abstract the first hydrogen atom. So we have seen this last time with the slide concerning the NOx behavior. So heptane shows has a very low NOx number because it's easy. Here we can easily decompose heptane and easily produce H radicals, which is, if you have more complex structures, not so easy. So of course then the molecular structure decides about the ignition process. This intermediate temperature chain branching, so okay, I have explained already in detail. So here, of course, then the formation of this hydrogen peroxide is the important part, and then we get the production of OH radicals. So now we have discussed hydrogen. Yes.
What was M? The M stands for M.
M is a collision partner, mainly water, but also oxygen, nitrogen, argon can also be a collision partner. So a partner which collides with our molecule, but do not, take part of the reaction, so it's not changed. So here we have a classical third body collision. So H plus O2, if they only collide, nothing will happen. So, but they need the third partner to bring them over the cliff, so that finally we will have HO2. So carbon monoxide. Okay, the global reaction here is CO plus O2 gives carbon dioxide. But this classical reaction path, so CO plus O2, CO2 plus O, and CO plus O, and collision partner gives CO2, of course, is possible, but this is a very, very slow reaction. But if only traces of water are present, we always have some OH radicals, and this reaction path here, so CO plus OH gives CO2 plus H, and CO plus HO2 gives CO2 plus OH. This is much faster. And therefore, for example, if you look for explosion limits of carbon monoxide, you always have to take care, is it dry carbon monoxide, or is it carbon monoxide with some humidity in presence. So you find totally different explosion limits here. Then the next molecule we have to consider is formaldehyde. So again, we have this global reaction. Formaldehyde plus O2 gives water and CO2. But of course, we have different reaction paths, reactions to consider here. So formaldehyde plus a radical gives an CHO radical plus RH, and so on. So different reactions have to be considered. And here, this formaldehyde gives carbon monoxide, which then can finally be oxidized to carbon dioxide. Now go one step further back. Now we will start with methane. So global reaction we have seen very often. CH4 plus 2 oxygen molecules gives water plus CO2. So when we look here, okay, CH4, when we look at the decomposition, one H atom is abstracted, so we have CH3. But then the question, how does this continue? And so here we see some possible reactions. So with O radicals, with OH radicals, and again with O2. And what you see, the end product here in this case is always formaldehyde. So we have seen when we start with CH4, we can yield formaldehyde, then we yield carbon monoxide, and finally we will yield carbon dioxide. So it's more or less a simple pathway. So here we have the methyl radical and CHO radical as intermediates here, but this is the way the oxidation of methane in a flame occurs, at least for lean mixtures, because for rich mixtures there is another pathway possible. So there is a recombination of CH3 radicals leading to ethane or this ethyl radical. So and this then gives another pathway, and here we end finally with the CH radical, which is then oxidized to CO. So we have a quite simple molecule, CH4. We have normally a very quite simple pathway, but unfortunately we have to consider, do we have a rich or a lean flame? Because in richer flames this is a dominant pathway. The flame then of course looks totally different. So, and then of course we can continue to larger hydrocarbons. And again, we have to abstract an H atom at the beginning. So the hydrocarbon interacts with other radicals, giving this hydrocarbon radical and other molecules. And then we have normally this beta decomposition. That's the then important step. So the this radical we have here. So we have, okay, we have an organic rest here, this R, and here we have the radical position, and it decomposes in a way that this radical here in beta position is or split up from the original molecule. So we have this alkene, and we have the remaining radical. So and this goes down finally until we have methyl CH3 radical and ethyl radicals, C2H5 radicals. So even if we start with a very long hydrocarbon, so C16, cetane as an example, as a diesel surrogate, finally it's chopped down in small molecules, and at the end we will yield CH3 or C2H5, which again take part here. So here we see the pathway again. So we start with a alkane, we get an alkyl radical which decomposes, giving alkenes and smaller alkyl radicals and so on, and finally we yield CH3 and C2H5. So when we summarize the chemistry part we have discussed today, so we have H2 oxidation. If we look, for example, at CO plus hydrogen or traces of water, whatever, we have CO oxidation plus H2 oxidation. Then we have this methanol oxidation, this formaldehyde part we have discussed. And then we can add also this simple CH4, C2H6 oxidation. And finally, we have larger hydrocarbons. So if we want to examine the larger hydrocarbons, we have to consider the rest here too. But if we know this part here, we can use this also for the other molecules. So we don't have to examine this again. So, and then again, we have to consider the temperature dependency. Again, at high temperatures, also for the larger hydrocarbons, this is the important reaction. This we have to know in detail, and this dominates more or less our chemistry. H plus O2 chain branching gives O plus OH. And in intermediate temperatures, so here from 900 K to 1200 K, we again have this different pathway. We form some hydroperoxide here, H2O2. This decomposes to OH plus OH. And this is then the dominant pathway at intermediate temperatures. And at low temperatures, it gets really, really, really complex. So I have studied chemistry, but I'm not an expert in chemical kinetics. And therefore, this for me is really not confusing, but it's, of course, you have to consider much more reactions. It's getting more and more complex because more and more complex molecules, especially this peroxide chemistry, gets more and more difficult. So here again, some details. So you have one peroxide already and add another O2 molecule. So we have some internal reconfigurations. You have chain branching, chain propagating. So it's very, very complex, and we will see it, I think, tomorrow with an example. These mechanisms then become, of course, bigger and bigger because you have to consider more and more species. But why do we have to consider it? So you can see this negative temperature coefficient, which is really astonishing, because we have seen that normally all chemical reactions can be described with an Arrhenius, or as an Arrhenius equation. So we have an logarithmic dependency of the ignition delay time over the temperature. So here we have 1000 K divided by temperature. So we increase temperature from here to here, and therefore the ignition delay time should decrease, because linearly in this logarithmic scale we would increase our reaction rate in our Arrhenius equation. But suddenly, when we look at larger hydrocarbons, we can see a behavior like this. Suddenly, we increase the temperature, but the chemistry or the ignition delay time increases too. So this reaction seems to be become slower. And then if we increase temperature again, we will come back to our expectation. Increase of temperature reduces ignition delay time. And this is here because the chemistry we have discussed before, we have different pathways. Different reactions are dominating different temperature regimes. So at low temperature, here maybe our peroxychemistry is dependent. Then here we have another reaction part. And then finally at the end, H plus O2 gives OH plus O. The chain branching reaction dominates everything. So this is why we have to consider complex chemistry. So first of all, we can have lean and rich mixtures. So the chemistry can be not totally different, but different reaction pathways can dominate. And finally, at different temperature regimes, also different reactions can dominate. So totally influencing here, for example, the ignition behavior. So here we see it again. So at low temperature, we have this complex peroxy chemistry. And then here at higher temperatures, here it starts already with the hydrogen peroxide branching. And at the end here, finally, we would have this H plus O2 reaction dominating the chemistry. And this is, of course, a complex network of temperature, but as you see, also of pressure. So especially then the third body collisions influence at higher pressures the chemistry. So how can we examine this behavior? So again, so here we have temperature and pressure. We have different regimes. So again, at high temperatures, we have this small radical chemistry. At lower temperature, this peroxychemistry. We have to look, can we examine these processes if we probe for proper molecules. And here, on these examples, we have to examine HO2 and OH. If this is possible, then maybe we can examine the ignition process in detail. So we can use, for example, a classical flow reactor here for the formation of HO2. So we have a reactor at a constant temperature in a range so below maybe 1000 K. And we have an inflow, the flow direction, and an outflow. And then we can examine, for example, the gas at the outlet. And this gives us, for example, information of this slow reaction. H plus O2 plus M gives HO2 plus M. At higher temperatures, where this reaction is dominant, we can use just a simple shock tube, where we can produce high temperatures and see very, very fast ignition events. So how can we do this? For example, we can use a specific laser setup. So we have here, for example, NH3 plus O2, and we use a laser to initiate the reaction, and we form some HO2, and which then can be detected. Here we have the detect the emission or the absorption. So we use a specific lamp here, and then the absorption at 230 nanometers is detected, and depending on the amount of absorption, we can get the amount of HO2. So using Lambert-Bersche law, so the light is going through our probe, and the absorption depends on the length of the cell and the amount of molecules in the pathway. So in a typical result we can see here, so the intensity as a function of time. So we initiate the reaction, and then we see how the HO2 molecule is formed as a function of time. Here we can see it at different temperatures, so the result for different temperatures. So a lot of experiments have been performed here. So with this, then we can finally get some more information. But we have to consider, when we have more complex configurations, like in this example, so we have complex peroxychemistry to consider. It can be very, very complex. Here we see it on the right side. We have different molecules at different energy level and so on. So we also have to use then complex modeling, which we will discuss tomorrow and discuss in detail next week. How to support chemistry here, or the experiments here, to get information about the reactions we have. And finally, one experiment where they have done this simultaneously. So we have one diode laser to examine the absorption of HO2, and we have a neodymium YAG laser to probe OH, and finally we get results for this one specific reaction of cyclohexyl plus O2. So we can examine different pathways within one experiment. So, but okay, so we are not experts in chemistry, so this is of course quite confusing, but this is the reaction we consider here. So it's cyclohexyl plus O2, and we have different intermediates here to consider, and we can have different outcomes. So different radicals or stable molecules can be formed, and looking at our experimental results from the former experiment, we yield information about the possible pathways we have to consider here. But again, it's very, very important to consider we also have sequential and direct pathways. It's very sensitive, and we have to consider it in detail. So the same experiment here again. Here we use an YAG laser at 282 nanometers to excite our OH radicals. We have a flow reactor, and again we initiate the reaction using a photolytic oxidation of cyclohexane. So this is in a high pressure cell in this example, but the experiment is more or less identical with the one we have shown before. We use a near-dim YAG dye laser system to examine the OH radical, and here we have an X-hammer laser maybe to initiate the reaction. And so again we get time dependence OH signals. So the reaction, as I've said, was initiated at 193 nanometers. So at different temperatures, of course, we get totally different temporal profiles. But of course, with this information, again, we can examine our reaction here, cyclohexyl plus O2, to get more details. And finally, we have the possibility to use a mass spectrometer, which also gives, of course, very detailed information what is happening inside our reaction zone. So here in this example, we have this flow reactor. We used again a laser to initiate the reaction. And then on the right-hand side, you see a mass spectrometer. So we suck some part of the mixture into a mass spectrometer and analyze then the mass of the different molecules we have in this specific region. So you see we have quite different experiments in different reactors, and altogether we get information of the possible reaction pathway in total, but also for some specific reactions we can yield very detailed information about the reaction rate at the given temperature and pressure. So of course we have then to combine all this information to get finally an outcome. And the problem is, you can see here, when we look at global combustion mechanism, so it's a quite simple molecule, CH4. It's quite simple outcome, CO2. But we have a lot of different intermediates. We have a lot of possible pathways. So to describe CH4 oxidation properly, we need around 40, 50 species and 150 to 200 elementary reactions. So it's getting quite complex, even for such a simple system. And it's getting much more complex if we have to consider soot formation. So we start with quite simple molecules here. So this is an pentane plus O2, and we get different intermediates at the beginning, and this form simple aromatics like benzene and so on, and this increase to PAH, and finally this coagulate together to form large soot molecules in a range of several nanometers. And so So of course, when we consider CH4 oxidation alone, which is quite complex, if we look at this possible way, we have to consider thousands of intermediates and so on, thousands of different states. So it's quite complex to describe this. But of course, we can look at this beginning. This propagule radical we have here is very interesting. So the reaction kinetics of 3C species at the beginning, this is very important for the formation of soot molecules. This propagule radical T3H3 recombination is the first step to examine this. So this propagule radical, due to recombination or addition, forms the first aromatic ring, and this then grows further on to PAH, and then finally to larger soot radicals. So here, this is the molecular zone where the reactions dominate on the molecular level, and here we have a particle zone where also the collision of different soot particles may form larger soot particles. And of course, this initial part is very, very important. But again, we have to consider it's a multi-channel reaction, or we have multi-channel reactions with complicated temperature and pressure dependency, and but we need this experimental data to examine this theoretical considerations we have here. So how do these two propagule radicals recombine to form finally benzene? It can again, of course, have different pathways. So there are then possible assumptions which we can see here. And then the question is, how can we examine this quite complex system? And again, we have the possibility to examine H atoms. We can examine propagule radicals using UV absorption, and we can use laser-induced fluorescence and laser-induced incandescence to examine the formation of the larger radicals, so or larger molecules, PAH, and finally the soot itself. So first of all, we have to produce high temperatures, so we can use the shock tube again. We have to produce radical sources, so we can use different molecules here, and we have our detection schemes I have explained before, and we have to consider different temperatures, different pressures, and different initial concentrations. So this is a classical result we can see here. So again, the formation of H as a function of time, which helps us to understand this specific equation here, the second abstraction of an H radical from C3H4. So we can use different reaction rates at different temperatures and different pressures, of course. Then we have the second, or the next abstraction leading to this propagule radical. again at different pressures and temperatures we can yield the reaction rates. So this is quite helpful, of course, to get information about these two important reactions. But then we come to the more complex situation, the recombination of two propyl radicals leading to benzene. And so here we can use examine the intensity. So we have propyl iodide, T3H3 iod, and this we photo ionize using a laser, and then we can examine the recombination of the formed propyl radicals, and so from this decay here we can get information about the reaction rate. And again, this is temperature dependent, pressure dependent, so we can see here a lot of results for this specific reaction. So I hope I have shown you that even when we have this very, very, very complex system leading to soot formation, we can, or we have the possibilities to look at specific reactions to get information about their specific reaction rates, and we can look at different steps of our reaction pathway, so the formation of our radicals. So here in this example, propyl radical, so from C3H6 propane, we have different steps to come here. That's the first important part, and then the recombination, the addition of two propyl radicals leading to benzene can be examined, and so on. So we have different experimental setups. We can use them to examine this. So flow reactor, I have explained already. We can use a classical combustion bomb, so where we have a premix mixture which we ignite, where we can examine pressure development, we can look for specific species, and so on. And we have this classical shock tubes where we have a driver part where we have a high pressure. Then we expand this high pressure in the driven part, and so we have a shock wave going through our system, heating up the unburned mixture. And normally we have this shock wave hitting at the end wall and going back, so heating up again our system. And this compression wave, shock wave, then initiates, of course, our ignition process. And we know normally exactly the final temperature before ignition takes place. And the last experiment is our rapid compression machine, where we can examine the ignition process at intermediate and lower temperatures. So we compress our mixture, giving temperatures in the range of 600 to 1000 Kelvin, and then we examine the subsequent chemistry which takes place. So this is a classical example of a shock tube. So at that time, our ignition takes place. The ignition is initiated. So then it takes some time until chemistry decides, okay, I want to ignite, and we can then see a sudden pressure rise, and this is then the final, the outcome is then the ignition delay time for this experiment, depending on our initial conditions before ignition. We can use this combustion cell for forced ignition. So we have a spark plug here, 2 electrodes where we have an electrical spark, which then initiates our ignition. Here we can examine the ignition energy. We can yield information about flame velocities, but also we can examine some more complex chemical species, so OH radicals or sooting, or we can use laser techniques, for example, to measure temperature. So here an example. So we have here we initiate a spark. The spark heats up very fast our initial regime, and then, for example, at the beginning, a pressure wave leaves our initial system. So we can examine, for example, how large is the spark as a function of time, and where is our pressure wave. And both quantities, so the radius of the kernel and the position of the pressure wave as a function of time, depends strongly on the ignition energy we use. So we can continue, check if it's working, but of course we can ignite, try to ignite, in this example, propane, C3H8, and of course there is a limit value, minimum ignition energy. Below this energy we won't see an ignition, and with higher levels we can see an ignition. Then we can examine, for example, the flame front position from using, for example, OH LIF spectroscopy. Compare this with numerical results, and from this we can get, for example, the global flame propagation velocity as a function of mixture composition. So these experiments can mainly use to get finally laminar burning velocities. And we can use the laminar premix flame. So we have an unburned mixture coming from the left with a given velocity. And then here we have our reaction zone where the reaction takes place, and at the end we have our exhaust gas. And we can use, for example, again our mass spectroscopy to look at specific positions of this process. So to examine, okay, what is in our exhaust gas, but more important, which intermediates I can find in the reaction zone. So, for example, if we look at a typical burner at different heights, this way, sorry, for different temperatures, using different hydrogen amounts here and flow velocities, we can see so the temperature depends on different factors, and also from this we can yield flame velocities, for example. So here we can see flame velocities for typical hydrocarbons, depending on the mixture composition, the fuel-air ratio we have. So near the maximum, or near the stoichiometric composition, we always see the maximum, and then the flame velocity reduces here for different hydrocarbons. but we also can perform much complexer experiments which SAT is set up. So here we have this mass spectrometer attached to our laminar premix flame, and we can examine then for specific configurations the amount of intermediates at specific conditions. And I think we come to an end for today. So we can use such a counterflow diffusion flame. So where we have an oxidizer coming from one side, the fuel from the other side for this configuration. So we have a flame which is for this diffusion flame configuration, we are located near the area where both flows meet each other. And of course, depending on our outflow velocity here, we have a stretch of this flame towards the outside. So we can examine, for example, extinction limits at which strain rate the flame no longer can exist. We can yield flame velocities, but again, we also can examine complex chemical reactions. So here, for example, so the strain rate and the equivalence ratio, when we look at this for H2R, we can see that at lower equivalence ratio and at a higher equivalence ratio, lean and rich flames, a lower strain rate is enough to extinct our flame, and at specific conditions, even at very high strain rates, we have a stable flame. So that's it for today.